Good morning, everyone. Good morning. So, how was the fondue? Who has been suffering because of the fondue? The first person I met coming in this morning said, I slept exactly 12 minutes. The second said, I slept exactly 1 hour. So, maybe it's not because of the fondue, maybe because of the company, but anyway. I hope you enjoyed the party yesterday night. I guess that the decision was already taken to redo it next year, maybe in an even more expansive form. Okay, we have a long day ahead of us, but also an interesting day, very interesting, I think. But I also need to tell you that one speaker unfortunately has cancelled. He is in bed with fever, and there is Henry Markram, who was supposed to be the second speaker this morning. I guess we will twist his arm to make him promise to come to us next year, and maybe give a better, longer speech than what was prepared to do, I don't know. We will see. Anyway, let's get started. The first speaker this morning, the first time I heard about him, I didn't know if he was incredibly smart or incredibly crazy. And then the first time I met, I knew he was also a bit crazy, but certainly very smart and courageous in exploring where humans end and where machines start. In trying to go around and figure out where that interface between human and machine is. Doing things like implanting microchips directly into his nervous system, and through that connecting it to a computer and through the internet. He's also funny in the way Brits can be funny. So I expect a great session. Let's go ahead. Kevin Warwick.
I like this funny the way Brits can be funny. I think I'm going now. Okay, what I want to talk about is the main bit of research that I'm doing. Just try and give you some reason for that and try and tie in some of the other work. I mean, other projects that are linked to it that I'm involved with at the moment are we're culturing neural tissue. This is neural tissue originally taken from rat brains and growing it in the laboratory and linking it to robots. So we now have robots that don't have computers for brains, they have biological brains. And I think that is going to affect the world in years to come, that you may in years to come get into your taxi in Geneva and it's going to be driven by this cultured neural network rather than a human taxi driver. The other thing I'm working on is with Parkinson's disease, with the deep brain stimulators, and we're trying to make them more intelligent to predict when people are going to have tremors before they have tremors. The same with epilepsy, trying to predict when epileptic fits are going to start before they start so that signals can be sent to stop them happening. And this is with my research, partly it's therapeutic, partly it's to help people with different disabilities, but partly it's also looking at enhancement, at improving, at upgrading. And I think if I show you this first video, this is a video Campbell aired. He lost his arm due to cancer and he's been given this articulated arm. But you can see with his left hand, with his human hand, he's pressing a button to operate the robot hand, which seems a bit silly really. What would be much better is if he could just operate this his robot hand directly from his brain, clearly. But that needs an interface directly from his nervous system, from his brain, to the wires in the arm, and potentially back the other way. Signals from the robot hand can be sent back up the wires onto his nervous system, onto his brain. So it needs an interface connecting his nervous system to the wires. Now that's great. We can see here the possibilities of helping someone who's had their hand amputated or their leg amputated or whatever it happens to be. Therapy. Once we've got signals on the wires here, we're talking of brain signals. We're talking of neural signals. And once you have signals on wires, you can send them where you like. So we can put some banana clips on the wires in this arm and send those signals across the internet, maybe out on a satellite, to wherever. But these are brain signals. These are neural. Now, your brain signals, your neural signals are within your body. Here's an example of my brain signals doing something now, controlling my arm. But I can connect onto my nervous system via an implant and send those signals somewhere else. So my brain can control something wherever those wires take me, wherever the internet takes me. And if there are sensory setups measuring different signals wherever the internet is connected to, then if my nervous system is connected up to that, I can sense things not close to me, but wherever. And similarly here, we can send signals back onto the wires, back up to the individual's brain to extend the sensory range. And of course, humans have this very limited sensory range. We have 5 senses. Our vision is okay, but it's a very, very limited range. There's about 95% of what's going on around us here we have no concept of because we just don't sense it. Why not try and extend our sensory range? I had 2 implants in my life. The last one of those, this is the picture from it, hopefully. There we go. As me on the operating theatre. So just to explain, I didn't have to have this for medical purposes. This was for scientific purposes. We had a team of 4 neurosurgeons working with us. It was a 2-hour operation. And what they did was fire this little device into the nerve fibres in my left arm. This is 100 electrodes. The Americans later called it a brain gate system. I was the first human, I think I'm the only alive human to have one of these implanted. And 100 electrodes. Each of the electrodes is about 1.5 millimeters long, so we're talking very, very small. And this was fired into the nerve fibres in my left arm. They're about 4 millimeters in diameter, to give you some concept. The total number of, they're very, very small, about 4 millimeters in diameter. The tips, just to give you some numbers, the tips of the electrodes are about 1 to 3 micrometers across. And neurons, your brain cells, mine, typically about 2 micrometers to something like 20 micrometers. Maybe if you're really cool, you might have a 30 micrometer one if you're really pushing it, but typically 2 to 20 micrometers. So neurons are micro scale, and they're not nano. That's important to realize. And this is a micro scale implant. And just to give you, hopefully you haven't had too much for breakfast, or too much last night, so we'll find what you had. This is a sort of a watered-down version from the operation, and this is my left arm at the time of the operation. What they did, first of all, they made 2 incisions, which you can see, and then pushed a sort of big metal bar up my arm called a Roberts to make a tunnel. They then pushed that tube down my arm, and that array, that 100 electrodes, they pushed down the tube. They then removed the tube to leave that array, which they fired into my nervous system. A little pneumatic hammer, bang, 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 in it went. And they then stitched it all up, and I had wires going up my arm. And you see that the little green connector pad that the surgeon's holding, that has electrodes on it that were effectively connected into my nervous system. And I was like that for just over 3 months. I had these electrodes out of my arm that we could just plug me into the computer, or I wore a little, quite fancy gauntlet arrangement which gave me a radio remote link between my nervous system and the computer. But it was bi-directional. Just to be clear here, some others have done research just monitoring what's going on. We were looking at stimulating, sending signals to my brain, as well as monitoring the signals on my nervous system. But it did mean for 3 months my nervous system was sort of out of my body partly, so I had to watch if I had a shower or a bath that I didn't get water on it, otherwise I would have short-circuited my nervous system. So we've got there's a discovery clip, which is quite funky music, just to show you some of the things that happened in the experiment. What we're trying to do, I would move my hand, generate neural signals that we could measure, just as if somebody, if they were paralyzed, they had the same implant in their brain, they could generate exactly the same signals. So some of what we were doing was assessing the technology for people with disabilities, for spinal injuries, for example, but also looking at where else we could go with it. There's sound on this, please. Have we got the sound? Oh. Let's read. Do you think you could? Yeah. I'll talk through. It may be on the computer. Just needs the mute button. I'll go back to this the thing with you. So just what you're going to see in the video, I hope. And here a little bit of as well, with extra bit of luck, is with my nervous system linked to the computer and then onto the internet. And I think at the moment, I don't know that anyone else has yet linked a nervous system or brain onto the internet. We did it in real time, so it was live on the internet when we did it, which meant that if you had known what the IP address of my nervous system was, you would have been able to send information directly to my nervous system, to my brain. The security we applied to it was that we didn't tell anybody what we were doing until afterwards, so nobody knew. Yeah, spam could have been a problem. Got right, yeah. Spam in a big sense there. So, I mean, it does raise questions down the road, clearly, for, if we all had our brains linked into the internet, for hackers and spam and all that, would mean a completely different thing. But for doing research of one-off projects and things like that, you can get away with it, I guess. Take a few risks. Are we okay for the sound? Okay. It should just be if it's a mute button or on the side of the... What I will do in the meantime, I will flick through the video. Sorry about this video, a big build-up, and you'll all expect this wonderful video. I will flick through the video, and we will go to some holiday snaps, and then hopefully at the end we'll... Right, these are some highlights from the experiment, just to show you what we're doing. On the baseball cap, ultrasonic sonar sensors. The output from the sensors was fed down onto my nervous system. You see this fancy gauntlet arrangement. An artistic guy in North London put that together for us. It is actually a radio transmitter receiver unit, so it was linking my nervous system to the computer by radio. So we got sound problems, or?
Yeah, there's sound problems. Can I get the mic? We got sound problems. They're actually switching off your presentation, so your pictures, for a few seconds. Okay. And then bring it back.
Okay, well, I will talk through this one. Yeah. So what you were seeing a second ago were ultrasonic sensors on the baseball cap. The output from the sensors was fed down onto my nervous system. What was happening when an object came closer, my brain was receiving an increased frequency of current pulse. So my brain was being stimulated by pulses of current of about 80 microamps at 40 to 50 volts, if you're interested in the technical bits. But the pulses were increasing in frequency the closer an object came, and the further an object went away, the pulses died away. So with a blindfold on, I was able to move around and detect objects. I didn't know what they were, but I could detect there were objects there, and pretty accurately how far away the objects were. In the picture, you saw Ian, my researcher, bringing a board towards me, what I was trying to do in the experiment was to stay the same distance away. So as he moved towards me, I would move away from him ultrasonically. I was trying to keep this frequency of pulses the same, so it didn't change. In terms of saying what did it feel like or whatever, well, it felt like something was coming close to me or was further away. So it wasn't like I was feeling pain, or it's like asking what does it feel like to see something. Well, you just see something. So in this case, it was extending the sensory range by means of the implant. We'd commandeered nerve fibres and used them for our purposes. And in this case, we were using extending the sensory range, or it was an extra sense, if you like to look at it that way, in terms of sonar. Are we okay for the... I mean, I'll show the video.
We should be okay now.
Okay.
Let's try.
Let's go for it.
Hopefully.
Well, I will explain what's going on. We seem to have
That's
a few...
very bizarre.
Yeah. If you all had implants here, there would be no problem. We'd be able to... We wouldn't need sound anyway.
As long ago as 2002. For 3 months, a silicon chip was implanted into the nerve.
Okay, we started from the beginning.
Oh, okay.
We have the sound.
Here we go. It's well worth it.
Yes.
In tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm. The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment. Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain. When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system. It was the first time two people had electronically communicated by thought alone. In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it. In 30 years, he believes we'll all have chips in our brains. But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies. We'll be half man, half machine, with super memory, super senses and superpowers. I think quite clearly that's where we're going. Superhuman. So be warned about that. Oh, thank you very much. Thank you. See, it was worth waiting for after all. This is my wife again. She's wearing here some jewellery that a student at the Royal College of Art put together. You could call it wearable computing. It changes colour from red to blue, and it was linked directly to my nervous system. Now, you can operate it in a number of ways. One, just hand movement, changing the colours red to blue. But also on the nervous system, there are all sorts of other signals. For example, if I was to go, ah! Shock. If I had been monitoring your... Sorry if I woke anybody up there.
If I'd been monitoring your nervous system, I would have seen physical indications of the fact you were shocked. Excitement is another one. So now picture the scene. This is linked to my nervous system, and this is my wife's jewellery, and when I am calm and relaxed, the jewellery is a cool blue, and when I get excited, the jewellery starts flashing red. So there she is in her office. She works a completely different place to me. Jewellery is blue, no problem. He's not doing anything he shouldn't. The jewellery starts flashing red. What is he doing? And more importantly, who is he doing it with? So I don't know whether it's a good idea, but there we go. This is a picture of me in, see, I told you, holiday snaps. This is a picture of me in Columbia University, New York, where they filmed Ghostbusters and things like that. This is the real-time computing lab. This is where we put my nervous system live onto the internet, literally plugged me in for a morning. And we connected up to the robot hand back in Reading in the UK. So I moved my hand in New York. My neural signals, my brain signals, were transmitted across the internet to move the robot hand in the UK. Now the Americans have done this with monkeys and rats within America. We were doing it with humans across the Atlantic to move a robot hand. The robot hand mimicked my hand movements, and this is the extra bit, fingertip sensors in the robot hand. When they gripped an object, signals were sent back across the internet to stimulate my nervous system in New York. So my brain was receiving this frequency of pulses, increasing as the hand gripped an object more and more. And what I was trying to do was to get the hand to just hold an object, like the egg test, which it did very, very well. We were able to get about 6 or 7 signals, neural signals in parallel in order to get very, very fine movement. Just open and close. There was not dexterity, but just open and close to apply pressure to an object. Which clearly for somebody who's had their hand amputated, this is good news that in the future they should be able to control very fine movements, an artificial hand. But here, this was my brain controlling a robot hand across the internet on a different continent. To all intents and purposes, my body stretched 3,500 miles. So the whole concept of what the body is really is going to have to change. If you wire yourself into the internet, your body is much, much longer than it is now. It's not restricted to the physical entity that you're used to. For me, though, the most exciting part was with my wife again. Now, just to be clear what she had, this is something you can try tonight if you've got a spare few minutes. She had electrodes pushed into her nervous system from the outside. This is a process called microneurography. So tonight, when you've got a few minutes to spare, get some very, very thin wires and try to push them into your nervous system for scientific purposes, of course. Now, you will find it is extremely painful. And we thought that she was going to get some anesthetic for this. But the doctor said, no, I need to make sure I've made a good contact here. So he pushed the first electrode in very gently, because there's very thin wires and they tend to buckle quite a bit when you push them in. And eventually my wife screamed when it hit the nerves, and the doctor calmly said, I think we've made a good contact there, that's fine. He then pushed another electrode in, so she had 2 electrodes, and we went back to the lab and linked our nervous systems together. I had the implant in place, so we linked our nervous systems together electrically. So literally what happened, when she moved her hand, if she went chunk, 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 I couldn't see what she was doing at all. We had blindfolds on, we had people checking what we were doing. She moved her hand, chunk, chunk, chunk. My brain received 3 pulses, chunk, chunk, chunk. And I knew that I was connected to my wife, and that's my wife sending me a signal. And it worked very, very well. So, and the same the other way, slightly differently. When I moved my hand, my wife received pulses on her nervous system. She described them as being, it was like lightning running up her hand, was her description. So it's nice to have that effect on your wife. What we did was a telegraphic communication from nervous system to nervous system. If you remember how the Morse code telegraph system worked, what we did directly from nervous system to nervous system. In the Discovery clip, it described it as thoughts. It's perhaps a bit strong, but it's television for you. But I can see where we're going, and my research in this area is now moving from the nervous system to the brain in order to do this experiment, again, directly from brain to brain, in order to communicate. Literally, then it will be by thoughts. Because here, why should we keep communicating in this pathetic way of having complex signals that we convert to trivial coded messages, either in terms of writing, like a lot of you are doing now, these trivial messages, or speech, is not really giving any indication of what we're originally thinking about. Why not link our brains together and communicate in terms of ideas, colours, concepts, all sorts of images? Let's communicate that way. Let's upgrade as humans instead of staying in almost like with the dinosaurs. Let's improve and use technology with us in order to move forwards into the future and communicate in a respectable way. Thank you very much.
Stay there, stay there, stay there. Don't go away.